Hi everyone. So we have been talking now about linear second order equations, and let me write you down how they look like. In the standard form they look like this, right? So this is linear because both in y and y prime they are only there in degree 1. But general second order equations could be much more complicated than this. But even these are hard to solve in general. And so we have so far not really seen any methods. Sometimes I gave you something, these were like what is called ad hoc. We were using techniques that for some reason or another that we still don't really understand worked in this particular case. But in general, we want general methods that work in all cases. Now, as I said, these even homogeneous ones are not easy to solve at all. I will talk about them later. But now, so look at the words that we have in this title here. Linear second order equations, homogeneous, so we're going to take f equals 0 in these particular ones. But there is also something here with constant coefficients. So that's an extra, what does that mean? So here p and q are considered the coefficients, but they're not constant because they depend on x. So constant coefficients would mean something like y prime plus by plus y double, sorry, let me write it again. It's a second order, right? So I didn't write the second order here either. Oh my god. Okay, I hope you all caught that before me. Okay, so y double prime plus by prime plus cy equals, and since we're doing homogeneous, I'm going to put 0. Later we'll put something else here in 5.4. So here b and c are now constants. In other words, do not depend on the x, the variable. Now, this is one form. Sometimes we have also, we like to write it, for instance, if we don't write fractions, sometimes we write it this way. And so here now a, b, and c are constants. Okay, so one of these two forms you will see, both are considered, they're the same, right? Okay, so how are we going to solve this? And this is actually extremely simple. Okay, and what it boils down to is, so the step 1 is, so you know that since it's homogeneous, there is no complementary homogeneous equation. It is the homogeneous equation. So now we have something that is similar, but it's called differently. So it's called the characteristic equation. Characteristic equation. Okay, and what is that? So we have, and I'll take the most general form here with a, b, and c, because then you probably recognize it even easier. The characteristic equation of a second order equation with constant coefficients. We need constant coefficients here. That one is the corresponding second order algebraic equation, quadratic. So what does that mean? I'm going to replace, so we replace y double prime with t squared, y prime with t, and y with t to the power 0 if you want. So if you want to think about this a bit, instead of taking derivatives, we're going to take powers now. So this becomes a t squared plus b t plus c t to the power 0. That's of course just 1, right? So this is now the quadratic equation, is a quadratic equation for second order. If you would have a higher order, then it would be of that, the order would be the same as the degree here. So that's a quadratic equation. And now a quadratic equation, so quick review. I mean, we have seen, and you have seen in your past algebra courses and whatever you have studied, many methods of solving quadratic equations. And one of the reasons is because they are, as I said, first order equations are very important differential equations, but more generally we see second order in physics, in other sciences. And some of these are actually constant coefficients. So then in that case we're rather lucky. And so the way to solve them is with quadratic equations. And so what is the quadratic equations? We have the quadratic formula, right? So the quadratic formula This always works, but it's not something you always want to try. But let me just write down the formula. It says the solution t, there are two solutions always. It's minus b plus minus square root of b squared minus 4ac divided by 2a. Okay, that is the general format. And we know that there is a couple, that this square root here is a little bit of a problem, because there are three cases. So the first case is, the usual case is that if this is, I mean, the case that you, in the lower level courses, it was always a positive. We call this thing, by the way, this has a name, this quantity here, this quantity is called the discriminant. And so if the discriminant is positive, then we have two real roots given by the formula, because we have a positive and a negative square root. But what happens if the discriminant is 0? Let's think about it. That's actually also an easy case, and it's a case that you also have seen a lot, is that if this is 0, there's no plus or minus, there's only one solution. So then we have a single solution, is a single solution, and the formula, of course, is then just minus b over 2a, right? Here, it's, so the two real roots are given by this formula, but let me copy the formula one more time. So minus b plus a minus, and the two come from the plus, you take the one with the plus, and you take one with the minus, right? Okay, over 2a. So single solution, because there's only, the square root is gone, right? So there's only minus b over 2a. And then there's a third case that only perhaps in 1375 you have seen, that is the case when this thing is, that's not true, 1275 you see this too. If this is less than 0, and what happens then? We have two complex solutions. Because what happens now? Well, in that case, this inside the radical you have a negative number. So you cannot really take the radical of a negative number, not at least as a real number. It becomes a complex number, or rather an imaginary number. And then we still have two solutions. So the two solutions would then be minus b plus or minus I square root. And here now, of course, comes the absolute value of this thing. Okay, this is negative, so I'm going to take the absolute value. That's then a positive number. And divided by 2a. Okay, so these are complex numbers. It's the 2a is a little bit annoying, right? So I'm going to write it, split it. It is there, so I cannot get rid of it. So I'm going to split this in the part with an I and the part without an I. So here's absolute value. Don't take this formula too literally here. This absolute value here, because you're never going to use that formula that way. But I just want to show you what is happening here. What we get is this complex number has two parts, right? We have called this is called the real part, and this guy is called the imaginary part. Note that I didn't take the I as part of the imaginary part. I kept it kind of a bit separate. And so here we're gonna, for our purposes, I'm gonna denote this here by omega. And you will see later why this omega is important. So notice that we have again we set two complex solutions, right? We have a real part, that's actually for both, notice that both complex solutions have the same real part. And what about their imaginary part? Well, one comes with a positive sign, I times omega, and one comes minus I times omega. So this fact that they have the same real part actually has a name, and we call them conjugate complex solutions, but that's not important. Now, depending on which situation we are, we're gonna have a different type of solution. Okay. Now, rather, I don't like formulas, and I don't like to teach formulas, so this was just, let's say, forget about it now. We're gonna do this now our way, just on examples. Now, notice that there are other ways of solving a quadratic equation. You don't need to always use the quadratic formula, because it is a little bit a nuisance, a formula, right? There's factoring that we have seen. If you can factor, of course, this only works in this case. You can do the factoring. Sometimes, if the easiest case is a is 1, then we have, if we have a factoring method. If there are two real roots, If the rules are natural numbers, then that's in case if a is 1. If a is not 1, even then there's a method, then you're going to normally get 2 rational roots. Of course, it could still be real roots, right? So sometimes there's no way that you can factor. Another method, we will run into the methods as we get examples, is completing the square. And that works for all 3, actually. That's a nice method too, that sometimes can save you a little bit of work. Although eventually, if you, perhaps this is a long time ago, so you don't remember anymore, but the quadratic formula, how do we get there, was exactly by completing the square. But okay, all this now, I put this on hold and let's look at examples. So examples that now will explain everything. By the way, I haven't said even yet what the solutions are, right? But I'm telling you, they will depend on this calculation of this quadratic. So let's jump into an example right away. Linear constant coefficient. I mean linear. I have to say this. Linear constant coefficient. Sometimes one drops the linear part, but technically it's still a condition. And homogeneous, of course. So the step 1 is the characteristic equation. Okay, the characteristic equation is t squared plus 6t plus 5 equals 0. So here is an example of what I said. Don't use the quadratic formula for that, because what we need is 2 numbers that multiply to 5 and that add up to plus 6. Okay, and so the numbers that we do this is 5 and 1, plus 5 plus 1, plus with the plus signs. Okay, that's exactly what we want. Okay, that is equal to 0. So we find that our solutions, so what we describe this equation, what we're doing is we're solving it. Right? So we find t equals -1 and t equals -5. And so now we know that a fundamental system of solutions, remember that was fancy word for saying every other solution is a linear combination of those, is now given by the following 2 functions, e to the minus x and e to the minus 5x. Where does everything come from? Well, it's this minus 1 and this minus 5. Okay, these are the 2 solutions. So this is what it means. So this is a fundamental system. Why is it fundamental? Because remember, they're both solutions. That's the first thing one should check, but I'm not going to do that. But they're both solutions. So we can plug them in and you'll see it actually becomes 0. It is good to do this once. But let me not, I'll leave that for an exercise for you. And they are clearly what we would call linear independent. They're fundamental system because if you take remember what you needed to check was that the one divided by the other, or one is not a constant multiple of the other, but these are 2 different exponential equations. They're not constant multiples of each other. You could say, oh, that's not true, professor. -5 times this guy is this guy. No. Minus 5 times this guy is this guy. No. The 5 here is not a 5 there. It doesn't distribute that. Okay, so no. So these are really different, and therefore this means that the general solution, is of the form a e minus x plus b e minus 5x, where the a and b are coefficients, constants. And how do we find this constant? Well, of course, we have always initial value condition. I didn't put it down here. The initial conditions, and the second order is saying something at some point, in this case we will take 0, what the function must be, -1, and 3. This is to be -1 and this is 3. In the example, I'm just taking examples so that the numbers don't get weird. Okay? So we have this initial condition that I'm now adding. How do we do this? Remember that one is also a little bit work. So this was step 2 if you want, writing down step 3 now. How do we find them? So the initial conditions. Well, you plug in x is 0 in this equation, and that gives you 3. 3 is equal to a to the power 0 plus b to the power 0. So that's an easy equation, but that's not enough, right? From just one equation cannot determine a and b, but it's because we only used one equation. We have to also use the second one. How do we do that? Well, for that one we have to take the derivative of what? Well, of the general form that we have. So if we take derivative, and the only thing you have to think about here is the chain rule, right? So a, the derivative of e minus x is e minus x times the derivative of the inside function plus b, the derivative of an e function is the e function, plug in the inside function minus 5x, and then take the derivative of the inside function. Of course, I mean, this is something that everybody knows very quickly, so I'm going to write it now. You probably will write it right away like this, right? Okay. And now we plug in again. So plug in x is 0, then y prime is, what was it? Minus 1, right? So we are plugging in again. Minus 1 is minus e a minus 5b. Notice that plugging in, especially 0, of course, it does, the initial conditions do not have to be at 0, but if they are 0, especially for these kind of equations, that's so nice because we know what these things are. They're just all ones. Okay, so what do we do now? Well, we have these two equations here. So we have a system of equations. Let me put it together. A linear system of equations. And there are many ways of solving. Well, there's essentially two ways of solving. You solve for one and plug into the other. Or you do the method of elimination. I like the method of elimination, namely I'm going to add. If I add these two, why am I adding? Because then these two cancel each other out. Okay, so we get 3 minus 1 is 2, the a is cancelled, and I get b minus 5b is minus 4b, so I say that b is minus 2/4, that is minus a half. Okay, once I have 1, I can plug that into the equation here, so I get the 3 is a plus minus a half. This means that 3 plus a half is a, that is 7 halves. Okay, so we find our solution is y equals 7 halves e to the minus x minus a half e to the minus 5x. Okay? All right, so that's the first case, right? This was the case where we had two real roots. Now, let's look at a situation, what we have here. Okay, here's another one. So I'm going to do each case, give one example of each case, right? And then perhaps we can do one more to see. Okay, here again, linear constant coefficient, second order. So step 1, what is our characteristic equation? Okay, that is t squared plus 6t plus 9 equals 0. So we, again, this factors nicely. Of course, we don't know that, right? But in this case, you can try. Or let's try to see whether you can factor nicely. If not, then you start thinking about more complicated methods, especially the quadratic formula. That's the last resort, kind of. So, okay, we have two numbers that have to multiply to 9 and add up to 6. 3 and 3. So if I solve this, I get t equals negative 3. I get it twice. So actually, there's only one solution. Yes, that's exactly what we predicted, right? A single solution. Okay. All right, that's good. So what now? Okay. So from the previous case, we know that we're going to take that root, and that becomes the coefficient of e to the x. So step 2. So a fundamental system of equation solutions. So we don't really need to calculate here. It's just writing down exactly what it is. So e, and then this coefficient is minus 3, so minus 3x. Okay, so again, this minus 3 becomes this minus 3. We do this for both roots in the previous case, but there's only one root, so we only get one function. Is that enough? No, we know a fundamental system for a second order has to have two. What is missing here? Okay, and that is the new ingredient. What we have to add now is, and I'm just going to tell you this in the book, they calculated for you that this is how it comes out, but we know right away what it looks like. We know it will look like at, so this is the first one. Oh, no, that's not what I want to do. The other one is the same, but with x in front. X times e minus 3x. Okay? Is this a fundamental system? Well, first of all, it's a system of solutions. So I said, let's not check it, but I'm going to do it for this one here, because that might be a little bit strange that you say, why is that actually a solution of this thing? The first one, if you calculate, is rather quick to calculate. So let's do this. So what is y prime? There's a product rule. So derivative of the first, 1, copy the second, plus copy the first, take derivative of the second, so that is minus 3x e to the minus 3x, right? Y double prime, derivative of this one is minus 3 e to the minus 3x, plus, minus, it's minus, right? This is a minus, okay, let me write this as a minus. So we would have here, the derivative of minus 3x, the first factor is minus 3, copy the other guy, and then we have to take derivative of, we copy the first and take derivative of the second, but there's an x minus 3, so actually it becomes plus 9. 9x e minus 3x. Okay, let's plug everything in an equation. So we get, so I'm going to plug this in here, right? I'm just verifying. So this is verifying, which we don't do. You don't have to do this. I'm going to do it only once, and you're never going to do it unless you just to practice. But you don't need to do this. We know that this is going to be correct. But just checking it. So minus 3 e to the minus 3x minus 3. Oh, there's actually minus 6. So let's combine these ones, right? Minus 6 e to minus x plus 9 x e to the minus 3x plus 6 times y prime, that is e minus 3x minus 3x e to the minus 3x plus 9 times y, and y was x e 3x, e minus 3x. Let's see. This should cancel. Is this happening? Well, first of all, we have to expand here. This would be 6e minus 3x minus 18x e minus 3x. Okay, so what is this equal to? Well, let's look at like terms. There are two types of terms. The one e minus 3x and x e minus 3x. Let's look at the e minus 3x. We have a minus 6 with a plus 6, and that's it. So yes, they cancel. What about the x e minus 3x? We have a plus 9, we have a minus 18, and another plus 9. They cancel out, so all this becomes 0. So it checks out. Again, I'm putting this between brackets because that's not what we're going to do. So we know, so I repeat here, our fundamental system is e minus 3x and x e minus 3x. So if we have a single solution, a single root, then it's e to the power e x with the root as the root becomes a coefficient of x, and x times that guy. And this is a fundamental system because if you take the quotient of these two things, remember, one a multiple of the other. Yes, Professor, the second one is a multiple of the first one, but not a constant multiple. That's what makes it a fundamental system. Okay, so we know now that the general solution looks like a times e minus 3x plus bx e minus 3x. Okay, so now step 3, again, we had an initial condition, which I keep forgetting to write it down here, but so the initial condition was y0 is 3 and y prime 0 is minus 1. It's the same initial condition as before, I guess. Okay, so if I plug it in, so 3 equals, so here I plug in x is 0, y is 3, right? We get 3 is a plus b. Oh, no, be careful now. Because if I plug in 0 here, this guy is even 0. That's even better, right? So we get 3 is a. We have already the solution. But what about b? Well, we have another condition. If x is 0, then y prime is minus 1. So that means we have to find y prime. Now, that's also something that we have done now. Minus 3 a e minus 3x. But now here we have a product, right? So it is plus b times the derivative of the first is 1, copy the second, plus copy the second, and then take the derivative of the 3x minus 3x here, right? So what we have here, okay, so that's what we have y prime. If I plug in now x is 0, then we get the y prime is negative 1, and on the right hand side, the powers of e, these exponentials all disappear, so we have minus 3a, we have a plus b, and then here again this x, this term disappears. So that's our equation. But we know what a is. A is 3. So minus 1, minus 9 plus b. So we see that 9 minus 1 is b, that is 8. So b is 8, and so our general solution is y equals 3e minus 3x plus 8x e minus 3x. Now, very often people, because we have a common factor this out and prefer to write it this way. Again, it's not necessary, but it sometimes is more, you see better what's going on. Okay? Good. So, one more case that we have to consider, right? The one where we had, So we have now checked this case, we have checked this case, we see that the solutions are slightly different, and this one again will be different. So let's look at what we have here. Y prime, double prime, plus 4y prime, plus 13y equals 0, and again initial condition, y0 is 2 and y prime 0 is negative 3. Okay, negative 3. Okay, so let's start with this. So what is our characteristic equation? Is t squared plus 4t plus 13. So we would like to try to factor this. That's always what you try. So we need two numbers that multiply to 13 and add up to 4. But 13 is a prime number, so there's not many combinations. There's only 1 and 13 and minus 1 and minus 13, none of which give 4. So that already tells you, this might therefore not... If this doesn't work, well, there are a couple of methods. It's at the completion of the square. But let's jump right into the quadratic formula. So what is the quadratic formula? So I'll write it up again. Minus b plus minus b squared minus 4a divided by 2a. Now a is 1 here. That makes it a bit easier. So we get minus b, that is minus b is 4 here, right? So let's say b is 4, c is 13, and a is 1 in our case. So minus 4 plus minus b squared, that is 16, minus 4 times ac, that is 4 times 13, is 40 is 52, divided by 2. 16 minus 52, what is that? That is 36, right? So this is minus 4 plus minus, but minus 36. 2. So what we then normally do is the square root of a negative number is you shouldn't write it that way. We should write it this way, bring out the I and then take the absolute value. That was what what I was saying here with I was using in my description of the writing down the solutions, this absolute value, right? You don't realize it, but that's what you're doing, right? You're dropping the sign, and so you said, okay, bring this minus 1 out of the radical becomes an I, and then we have 36 divided by 2. So that is minus 4 plus or minus I times 6 divided by 2. Or even better, we can cancel. That is minus 2 plus I, 3I. Okay, so what does this now mean? We have two solutions. Let's write them out explicitly. Minus 2 plus 3I and minus 2 minus 3I. And so they are unconjugate because they have the same real part, but they have complementary imaginary parts, 3 and minus 3. Now, here, what is the solution? So step 2, and this is of course where it all comes down to. So a fundamental system of solutions. So you would say, oh, okay, let's do what we did before. It is e to the minus e, and then we put the root, so minus 2 plus 3i x. And this is correct. But what is e? What is an I in an exponent mean? If you remember from Calc 2, so I'm gonna put this between parentheses because we're not gonna do this calculation anymore, but just explaining this. So this is from pre-calculus, from 1375, or pre-calc if you took it somewhere else. So what is this? Well, let's work this out, right? So this e to the minus 2x plus 3ix, I'm expanding, and then we do what we often do with these sums of exponents. We take it e minus 2x times e to the 3ix, okay? Now, what is this guy here? So e 3ix, so okay, let me write it here, E3ix. We gave a meaning to that in 1375, and we said that is equal to, sorry, let me write this, not write this here, but write it here, that is cosine 3x plus I sine 3x. That's what is represented. I won't go over why this represents this, so this would give me e minus 2x cosine 3x plus I sine 3x. Now let's work again. None of what I'm writing now, since I opened this parenthesis, is something that you're going to do, but I just want to show you where it comes from. Let's expand. So e minus 2x cosine 3x plus I'm putting the I out first, minus 2x sine 3x. So we have a solution that is a complex number, a complex function. That's something we don't want. We don't want complex functions, we want real functions. And now it turns out that each of these, the real part of this solution and the imaginary part of the solution, both are actually solutions. So all this long story, I'm going to close my parentheses. So everything you can now forget what I said. A fundamental system of solutions. So wind back to where I wrote down fundamental system solutions and just say that is e to the minus 2x sine 3x, and e to the minus 2x cosine 3x. And what are these numbers? So now we have to make sure that they get the numbers correctly. The minus 2 is the real part. So this is the real part of our solution. And what is the other guy is the imaginary part, but the absolute value of that. We ignore the sign. It has both a positive and a negative sign, right? We look without the sign, so we take, that's the 3 here. That is the imaginary part. Or at least, well, the absolute value of that. So perhaps absolute value of the imaginary part. We drop the sign. We only look at one of the solutions in that sense. Okay. And again, these two solutions are not multiples of each other. I mean, sine and cosine are not multiples of each other. In fact, the quotient is a tangent, right? Okay. So what does this mean? This means that the general solution here is, well, a linear combination of these two guys, sine 3x plus b e minus 2x cosine 3x. Now, should I write the sine first or the cosine first? The book sometimes seems to write the cosine first because of this reason here, but it doesn't really matter, right, in which order I write this. Okay, so the last step, step 3 is the initial, or step 4, I don't forget now, I lost a little bit track of my count, the initial condition. So if x is 0, then so x is 0, then y is 2, so we get 2 equals. Now be careful, now you have to plug in two places there, the x, right? If I plug in 0, what happens is, the lucky part for us again is that this guy is going to disappear. So we're going to have only one term left, and also we know the cosine of 0 is 1, so that's also very easy. So this is b times e to the power 0 times 1. So e to the power 0 times 1, so this is just b, and so we have already solved it, b is 2. Okay, and so now we need also the other guy, so we need y prime. Okay, now be careful, this is a little bit more complicated because we do have derivatives here, products here. So we have derivative of the first is minus 2a e minus 2x, copy sine 3x, plus a to the e minus 2x, and now we take derivative of sine 3x is 3 times cosine 3x. Okay, plus we do the same here. Minus 2b e to the minus 2x cosine 3x plus plus b e to the minus 2x, and now this derivative of cosine is minus sign, so it's minus sine 3x, but there's an extra 3 here, right? Minus 3 times sine 3x, let's write it this way. And now we're plugging, so x is 0, then y was, what was it here? Negative 3 this time? Yeah, no, 3. No, negative 3. Is this a negative here? Yeah, it was a negative. It's supposed to be a negative here, sorry. Negative 3. So negative 3 is. Now let's see what happens. The sign we know is cancels everything. So sine terms never contribute. It's only the cosine terms. So this term will now contribute. So that is 3a. Oops. Right, because this will be 1 and this will be 0, so cosine 0 is 1. So 3a. Then another term with the cosine in, minus 2b, right? So because this will be e to the 0 will be 1, this cosine 0 will also be 1. And then this term again has the last term has a sign in it, and therefore it will be 0. So we have this equation, but we know that b is 2. So we see that it's 3a minus 4. This tells me that 4 minus 3 is 3a. So that's 1, so a is 1/3. And so with our solution, y equals 1/3 e to the minus 2x sine 3x plus, what was b? 2, right? Yeah, b 2 times e to the minus 2x cosine 3x. Okay. Again, it is common here to factor out the e minus 2x. So one can write this as e minus 2x 1/3 sine 3x plus 2 cosine 3x to just get a bit better view of what's going on. But again, this is not necessary, right? Okay, that's it. Okay, so what is it, the general? So perhaps here, let me write down a little bit again what the general solution is. So we have, if it in 2, if this b squared minus 4ac, the discriminant is less than 0, then we know that there are two roots, and they will look like, and I'm going to write it, I'm not going to write the formula, but we know how they look like. They're going to be of this form. They have a real part, what I now call lambda, which is the same, and they have an imaginary part, which is, one is the negative of the other. That's how it looked like in general, right? So let me go back to our quadratic equation that convinced you that is what I wrote down here, right? And I even called this, I said already, let's call this omega. I should have said also, let's call this lambda. So this we will call lambda. Okay, that is exactly, so that's where lambda and omega come from, right? But it's why I do this is because now I can write down in that situation, this general solution, how will it look like? Well, we have the lambda will be with whatever sign it has, right? Here lambda, it's e lambda x. In my example, it was minus 2, but so in general it's e lambda x, and then we have the cosine and e lambda x sine, and what is that? Well, it's this other guy, omega x. And that's why we use omega, because it reminds you perhaps of an angle or even amplitude. Okay, because this is really what it is, it's an amplitude. Frequency. The amplitude is the other guy, ELX, by the way. So these are the two solutions. Okay, and we know that every solution is then a combination of these two. So perhaps that is the one that you have to do a little bit more. Practice this a little bit, but I'm going to stop. I just want to do one example because it's a factory method that you might have forgotten a little bit. So let's look at this question here. 6y double prime minus y prime minus y equals 0, and this is an initial condition. y0 is 10 and y prime 0 is 0. Okay, so step 1, the characteristic equation. That's 6t squared minus t minus 1 equals 0. I hope you see that there's a minus 1 here, right? And then the y is replaced by t to the power 0. Okay, so this is how the characteristic equation comes. So make sure that you know how to get from a linear constant coefficient second order equation to the characteristic equation. Now this one here has an a that is not nice. It's not 1. So you might say, okay, I'm going to use the quadratic formula, and that is perfectly fine. And very often that's what you have to do. You have no choice here. But I want to remind you the AC method. So remember, AC refers here to A, B, and C. So A and C is 6 and negative 1. So what we calculate the product that is minus 6 here. The product of these two, the A and the C. Okay, that's negative 6. And then we do the same thing as with the normal factoring. Two numbers. So two numbers, let's call them red and orange. So if you take the red and you add it to the orange, you get, what do you get? You get negative 1, that is this guy, right? That's what you would do, right? The adding is the one that the coefficient of the linear coefficient. And what is the product of these two guys? If you multiply the two guys, so we are multiplying, then this should be, well, this number, minus 6. So we look for two numbers. So the AC, but this is the AC, right? This is AC and this is B. If you want this, write this in general A, B, and C's. So two numbers that add up to -1 and multiply to -6. Of course, we're going to look at the multiplication first because that rules out quite a lot. So, and here it's clear what to do, right? So if I take, let's see, minus 3 and 2, right? They multiply to -6 and they add up to -1. Sorry, it's a little bit small. So what does this now mean? So again, let me write it up. This is minus 3 plus 2, and this is minus 3 times 2. What do we do with that? Well, we write now -1, we split -1 in this way. So we have 6t squared. This minus 1, I'm going to write as minus 3 plus 2t minus 1. Now, be careful, do the right one, right? There are two minus 1, so get a bit confusing. It's the b that I wrote as a sum of two things. That b I'm going to replace, and I'm going to group. So we get 6t squared minus 3t plus 2t minus 1. So we group these two and we group these two, and we factor out as much as we can. In the second one we cannot factor out it, but here we can factor out the 3. So this is 3t, sorry, 3t. That's the whole point. 3t, and what do we have left? 2t minus 1 plus 2t minus 1. We have a common factor, 2t minus 1, that we can factor out, 2t minus 1. And what is left? 3t, and here, well, there's a 1 here, plus 1. And so this is our factorization. So what does this mean now? What are the roots? 3t plus 1 equals 0. That means that 3t is equal to -1. That means t is minus 1/3. And this means that t is a half. Okay, so what would, in this case, what does my solution look like? Step 2. Fundamental system. Well, now we have to think, which case are we in? Well, we are in the first case where we have two different real roots, and then we know that this is take each of these roots, they become the coefficients of x. Okay, which order, again, doesn't matter. So our general solution is a times e to the minus 1/3 x plus b times e to the half x. Okay? And now, finally, the initial condition. So if x is 0, then y was supposed to be 10, I guess, and the derivative was 0. So we need the derivative here also. Let's take derivatives, which is not so hard here, right? We know that what happens is from the chain rule we get this coefficients, these guys coming down, which are the roots, by the way. Okay. So if I plug in, so let me do the plugging in here. So if I plug in here, this becomes 10 equals a plus b, because again e to the power 0 is always 1, and here I get 0, right? This one is equal to minus 1/3 a plus a half b. Okay. Now you don't like fractions in these equations, at least, so we can multiply both with 6. So multiply this with 6 to get rid of the fractions. We get 0 equals 6 and 3 cancel, so it's minus 2a. 6 and 2 cancel, becomes 3. That's one, and the other one is a plus b. We can still do, let me show you how you do elimination. That's the one that is perhaps a little bit more advanced. It's prettier in some sense. So what do you do here? Well, adding will not be okay, because dotting cancels. What we need to do is we have to multiply this with 2, and this just add this to that one. Okay, so we multiply the top one with 2 and add, so we get 20. 2a minus 2a is 0, plus 2b plus 3b is 5b, and so we see that b is 4. If you don't like this method, do the substitution method. Now I can plug this in, so 10 equals a plus 4. This tells me that a is 6. So our solution is y equals a is 6 e to the minus 1/3 x plus 4 e to the half x. Okay? So this is really simple. You just need to know your quadratic formula and determine in which situation you are. Probably the one that you have to think a little bit more about is exactly where goes what is in this case here, right? So to write down these formulas, you have to find the real and imaginary part. But all that is straightforward. So notice that these are formulas. So we're not going to do the calculations anyway. Once you know this is what you do. I solved the problems like this problem. This is what you do. You just find the solutions, determine which case you're in, and write down the general solution and find then the coefficients using initial conditions, if there is such a question. Okay.